Thanks, Sarah. So yes, as Sarah said, my name is Gordon Lindsay. I've been with Tooth Suits for just over 12 years now. During that time, I spent a lot of time commissioning, designing and building control and data acquisition systems for national flow laboratories here at NAL, and also for commercial jobs with Tooth Suits as well. During that time, I've gained quite a lot of experience in working with digital data and analog data and how to design systems around that. And that's aided me in my current role, which I've been in the past 3 years at Tooth Suits, which is the Head of Digital Services at the National Engineering Laboratory Division. Working with data scientists and mathematicians to come up with data-driven models to help automate processes that ultimately help industries implement more efficient digitalisation strategies. We've actually presented a few webinars in the past, myself and the other team members that we've got here. And if you're interested in them, you can download them at any time using the links that I've got up on the screen just now. These webinars have tended to focus on more the data-driven modelling side of things. We're actually taking a step back today for this particular webinar, and we're talking about the prep work that goes into making a data-driven model, looking at the data itself, the sources, and just some of the kind of challenges that you might not expect if we're undertaking one of these kind of projects. So this is particularly relevant to anyone who's thinking of undertaking a data-driven modelling solution, either internally using their own skill sets or even planning to subcontract to someone else. Having thought about the things I'm going to talk about during this webinar always helps in that process and makes the specification process go a lot smoother for all parties involved. So as such, title of this webinar today is Digital Data Sources, Formats and Considerations for Use in Data-Driven Modelling. And specifically what I'm going to be talking about today is the different levels of a data science based kind of project. Data sources themselves, the storage of that data, how you can visualize it and work with it, and then the kind of applications that that data ultimately feeds into, which then feeds into the more complex models that we've spoken about in previous webinars. And just at the end, I'll give you a brief summary of what Tooth Suits can do in terms of our digital services platforms that we've got. Just to kind of provide some context for this webinar. As I say, I work at the National Engineering Laboratory Division. That picture up on the screen just now is of the James Young building here at NAL. And the systems that our teams have worked with over the years have all been designed and built in-house. As you can imagine, in a laboratory such as this, there's lots of different sensors out there. We are predominantly interested in fluid flow measurement, but of course there's secondary instrumentation, things like pressure transducers, temperature transmitters, densitometers, all feeding data back, all different ages, so analog and digital devices, all feeding back to control systems and data acquisition systems. So we've built up a lot of experience in how to deal with these different types of data and how to feed them into one system. And in the past 3 years, as I say, our team have been looking at how we take that data that we've been storing and do something new with it. So come up with machine learning models, data-driven models that can tell us something new about either our aging systems or something new about a new system that we've implemented. So just as just to kick off, and if you've seen me present before, you might have even seen me present this particular slide in the past. So this is just what I like to do in terms of clarifying some. We're working in a very buzzword-heavy industry, as I'm sure a lot of you listening to this webinar will be aware of. So things like Internet of Things, Industry 4.0, artificial intelligence, AI, these are all terms that sometimes even become interchangeable depending on what organisation you work for, or maybe your customer or clients expect these things to mean one and the same, but in fact they can be very different. AI in particular is actually misused quite a lot of the time. People talk about AI, but in fact what they mean is machine learning. So everything I'm talking about today is very much on the machine learning, data-driven side of things. Specifically, again, the whole point of these webinar series is to draw from your own experience. So my experience as a control systems engineer is very much around the hardware, and now I'm working with data scientists to help them interpret the hardware and the data that comes from sensors. So specifically things like digital field bus networks. So Modbus, Profibus, Foundation Field Bus all have different technologies which have adopted them over the years. You have to be able to account for all of them. Digital data itself that comes from sensors and data loggers and the server-client interfaces. When it comes to actually analysing data, we're talking about analysing large data sets, and that can be historical data that's been building up on a server and a facility for potentially even decades, or we're looking at live data where we're streaming data from one sensor or multiple sensors or an entire plant, and modeling with it live and seeing if we can do some automated prediction or condition-based calibration with it. Everything is ultimately about maintaining a facility or increasing the efficiency that maintenance is given, and increasing even the efficiency in staff scheduling. So when you think about a data science project, there's various levels that a data science project can be, and it all depends about what you're looking for as a client or a customer, or even in your own, if you're just looking at this from your own internal purposes. So we like to split things into 4 simple categories, and as you'd expect, the more complex the work that you're doing, data science or data analytics, the more costly it's going to be. And to start off, you've got data visualization. So data visualization, simply taking data and looking at it in a new way. A lot of sensors these days, whether it's flow meters or even just a standard pressure transmitter, can give off more than just the primary value of flow pressure. There's a lot of diagnostic data that can come off of them, and it can sometimes be overwhelming for end users to sift through all that data. So we're just finding ways to better visualize data is the first stage that we look at for some customers. But you might be more interested in diagnostics. So taking that data and actually telling end users something interesting about what that data is telling them about a particular process. You then go a stage further and you start talking about remote monitoring, so health assessment, so trending the data live, flagging up to end users potential errors that are occurring. And of course, the final stage is predictive analytics, not only telling clients about an error, but predicting when an error might occur based on the current trends that system's seeing. So yeah, and just a little bit more on that essentially. So with dashboards and alerts and data visualization, what you're looking at is giving clients and customers valuable insights that were not immediately obvious from traditional ways of trending graphs on Excel spreadsheets. Sometimes things can get missed, and sometimes correlations and data patterns can get missed as well. So we find it's actually quite a useful thing to do internally, never mind offering that as a service to others, but just from an internal exercise. Of course, then looking at data analytics and diagnostics, you are starting to build machine learning models, and analyze things like variable importance. So how important is a diagnostic variable, which seems number 20 down the list of all the variables that have been output. You may have ignored it before, but in fact that variable is actually extremely important in detecting when you've got gas in your system. And when you correlate that with variable X further down your list, then you can reliably predict what's going on in your system. So that kind of information can be useful as well. And when you're looking at remote monitoring, again, you're looking at data from instruments that a customer may already have, and training a model to actually automatically detect that error. And we'll talk a bit more about that as we go on to this webinar. And yeah, the predictive analytics, of course, is the most complex. It requires an immense amount of data to be able to reliably predict something. But when you do have a reliable system which is able to predict when an error is going to occur, as you can imagine, the efficiency that an end user or a plant can then implement is fantastic. So we talk about data sources, certainly from an engineering application and certainly from our experience. We're talking about individual sensors. Sensors themselves can have a single variable output, as I've already said, things like pressure and temperature. But as I say, multiple diagnostic variables are also available, which can complicate matters, but can also give clients very, very valuable insights into their systems. The signals themselves can, well, if you put simply, can be split up into analog and digital. Excuse me. Analog, of course, is your traditional 4 to 20 milliamp signal, maybe even 0 to 10 volts, or if you're looking at RTDs for temperature measurement, resistance. And then the more modern equivalents of these kind of devices have a digital transmitter on board and will give you an option for outputting over a field bus. And that, again, that field bus can be foundation field bus, mod bus, profi bus, even CAN bus. And all those field buses can, of course, be picked up by OPC and streamed to any system. Of course, and that can even be a distributed control system. So a PLC, a programmable logic controller, is taking in these kind of sensor readings, but it's also responsible for control, as I'm sure many of you are aware. So things like valve control and positional feedback, as well as pump, motor, set points and feedback. All that data is going back and forth and can be used to train data-driven models if interpreted correctly, and crucially, if stored correctly. And just to provide a bit of an overview for one of our own systems, it's entirely common for many facilities throughout the world, unless it's a new build facility, to make use of multiple field bus networks. And that can be for a number of reasons. It can be due to the fact that a particular subsystem is relying on a particular protocol, or it could be that staff and maintenance supervisors have changed throughout the years. They maybe have a preference to a particular protocol, and then during their tenure, they've implemented certain protocols. And what you end up with is a facility that has to deal with a number of these protocols. And this is an example of our facility. As a calibration lab, we have to account for these different protocols because you never know what kind of device you're going to get in. So we have Profibus for our PLC communication. We have ASI, actuator sensor interface, for the control of our valves and the feedback of our valves. We implement wireless HART and the variety of digital field buses I've already mentioned, as well as analog systems. And these get streamed to both a diagnostics analytics package for flow calibration calculations, as well as a traditional SCADA HMI system. And just for clarification, just in case those listening aren't familiar with OPC, so Open Platform Communications, I do refer to it off the cuff quite a lot, so I thought I'd just throw this in here just to clarify what I mean by that. So OPC ultimately facilitates data exchange between different field bus networks. It operates at the server level, and it basically converts read and write requests from manufacturer-specific formats into generic requests. So it's basically a translator that operates in the background, so you're not having to worry about whether a device is outputting Modbus, Profibus, or Foundation Field Bus, as I've shown in this example on the right here. And basically, if you've got a software package which is implemented in an OPC client, i.e. the thing is tasked to read the server and gather the data, the OPC client doesn't need to know that level of detail about the protocol or the manufacturer or even the device. All it cares about is the data that's been stored in that server. So it just streamlines things and allows for the free flow of information and makes things that bit easier when it comes to the data analytics stage and the data storage and historian stage. It's also worth pointing out, and again, it's quite crucial for when you're undertaking data analytics projects, that an OPC can be used to share hardwired analog signals. So imagine a pressure transmitter, which has been hardwired into an analog input of a PLC. That will then get stored in a data block, and then that data block will can output to an OPC server. And it's just, while the commissioning engineers and even some of the field engineers will be aware of that, if you then just export that data and give it to a data scientist, that information is lost about the root of that signal, the fact it's an analog signal, and therefore you've lost that bit of detail. And that becomes crucial, as I'll explain later. Excuse me. So as I say, when the data is stored digitally, the data behind that source can be masked. Famous myself here by giving that explanation in the last slide, but yes, ultimately, if you have got PLC, which is often up a digital value, if it was an analog signal, then and you're giving that to a data scientist, you as an engineer should be able to explain to them that yes, it's a digital value, but since it's an analog value, you should bear in mind that there may have been some electrical noise associated with that signal. So if you're seeing unusual fluctuations when you're doing your data analytics, bear in mind that it's an analog signal, and consideration should be given to the location of that sensor. Was it near a pump or a motor of some kind, which could have affected the signal? If the sensor is outputting a digital field bus signal and the application is time sensitive, and when I say time sensitive, what I mean by that is you don't want any data lag. Again, just drawing from my own experience working at a calibration lab where triggering of logging is very time sensitive and very crucial. You need to be aware of the associated lags that come with digital data output, so things like the sensor output, the OPC server, and the OPC client. And ultimately, yeah, as I've already said, this detail can help a data scientist develop a model that accounts for these real-world effects. You're not just blindly modelling data. If you're working with an engineer who understands this stuff, as we do in my team, we've got data scientists, mathematicians, and engineers. We kind of complete the picture, so to speak, and that really helps a model be more reflective of reality, as opposed to just blindly modelling data and outputting correlations that may not be representative or miss things like crucial information, like the fact it's an analog signal and it's next to a pump, and so on and so forth. And just to clarify what I mean by digital data lag, very simple example. So if you take, for instance, a flow meter which is outputting a digital flow rate over foundation field bus. Things you have to consider is, what is the data output frequency? How often is that meter offering up that information to the digital field bus network? What is the lag between the physical measurement that the device is carrying out, then going through the firmware calculation and then outputting the data? The digital networks themselves have different speeds associated with them. It's protocol dependent. And how often is that OPC server polling the device and the digital network for data, and how often is your OPC client or your data acquisition software polling the server? That seems like I'm nitpicking a bit, and it may well be for a lot of the applications that you're considering. It may not be an issue, but if you have even 1 second delay in all of these different stages, or even a 1 second delay total, that could still affect time-sensitive data acquisition and calculations, and certainly would affect us. So it's something to bear in mind if that's the kind of business that you're involved in. The data storage itself can come in different formats. I'm sure it would surprise most of you to know that Excel spreadsheets is still one of the most common formats that we get data given to us. It's common for legacy applications, and we ourselves, as the national standards, for the past 20 years, have stored all of our data in Excel spreadsheets, and that's how they sit just now in our servers. And also, of course, third-party data loggers. So instruments that have come with a, excuse me, losing my voice. Instruments that have come with a piece of software, so a flow meter that's come with its own bespoke software, and it's got a logger on it. It may offer clients the option to log that data and then output it as a .csv file. More modern applications certainly make use of databases, so SQL servers. And a SCADA historian, well, it depends on the package that you're using. It might be a combination of spreadsheets and databases. But the point I'm trying to get at here is the storage method doesn't really matter, because most data scientists and mathematicians will be able to work with any data you throw at them in any kind of format, as long as you give them a heads up of what it is you're working with. What's more important is the labeling aspect of data storage, and also having a consistent structure in the data that you're giving them. But things like consistent variable naming, that sounds obvious, but things like if you give them a spreadsheet, for instance, with lots of pressure sensors and temperature sensors, are all the variables auto-generated? You would hope so if it's an automated system, but some applications, variable names and even the data points themselves, they might be the results of manual inputs from an operator. So that's something to bear in mind. Are the variables even named? We've seen scenarios where we've got lots of data points, lots of numbers, and the columns are all headed A to B or 1 to 10. So things aren't often as simple as you'd think, even at this starting point, and you have to talk to your clients and you have to talk to whoever it is you're designing a data-driven model for to get a better understanding of the data you've been presented with, which can be quite time-consuming, especially if you're not talking to the right person or the person who's working with this data day in, day out. The crucial aspect as well is event labeling. So if you've been tasked to build a data-driven model, which is to automatically flag certain conditions, for instance, errors that a client might want to detect in their data, you need to be able to point them to where within that data these errors occur. So if it's time series data between time periods X and Y, we know this error occurred, therefore train your model to look for that kind of error. You also want to be able to tell them what a normal operating condition is, and also flag any unknown error conditions as well, just so that when you're training your model, you can better understand yourself what kind of patterns you're seeing in your system. So this has consequences in terms of your modeling. So when it comes to unlabeled data, that ultimately involves something called unsupervised learning, and it can be, or another way of describing that as anomaly detection. So you can still work with that data, but just the information you're going to get isn't going to be as detailed. So as you expect, anomaly detection is simply looking at the data, modeling it, and working out where there's outliers which exist with the normal trend of the data. Now, while that may seem simplistic, it can actually be quite useful as a first stage in understanding a data set. So say you've not been you don't have access to an experienced end user who can interpret the data. First stage you can do is run the data algorithm, even if it's on historical data or on live data, flag these anomalies, and then use that as your first opening gambit and speak to the operators and say, look, we've flagged all these red points here. Can you explain why this would happen on this particular device at this particular time? And that can be the first stage in developing a more intelligent model. Labeled data results in something called supervised learning, or a classification exercise. And with that, you can do a lot more with your model, and you can provide a lot more useful intel to your client ultimately. So an example on the left there, this is an example of a model that we trained using ultrasonic meters. And we wanted to detect when the meter was in normal condition, detect when it had a vertical misalignment associated with it, when it had been installed in some pipes, horizontal misalignment, and also any step change in the process. And I'm happy to say we were able to successfully develop a model that was able to correctly predict these events, and that became a very useful tool for the people that we did that for. When it comes to packages, again, if you're a data science company yourself offering packages, or if you want to understand what kind of packages a data science company such as NAL can offer, the unlabeled, unsupervised learning anomaly detection method is a package in itself. So that may be all you want to do. You may want to just flag anomalies and take it from there. You may then want that to feed into the supervised learning scenario and work with labeled data, or you may already have labeled data to hand, in which case you can go straight to this exercise. Ultimately, all these things can be packaged up together or one or the other and feed into a condition-based monitoring system or a condition-based calibration system. And again, just a point of clarification, when we talk about condition-based calibration, this is opposed to the more traditional method of time-based calibration. That's anything from a school laboratory through to an engineering application where, sure, it won't be a surprise to anyone that there's usually planned maintenance scheduled around requirements of different devices. There might be a biannual calibration or an annual calibration, but there's costs associated with that, and particularly in the oil and gas industry, where shutting down a pipeline, removing a meter, shipping it off for calibration, and then refitting it once it's been calibrated. Never mind the shipping fees and the calibration lab fees. It can be quite costly. So of course, people want to find a more efficient way of doing that if possible, especially if the calibration certificate comes back and says there wasn't any calibration drift, your meter was working perfectly fine as it was, and yet you're actually certified for another year, but ultimately you didn't need to remove it in the first place because the calibration is not drifted. What people want to do now is move to a condition-based calibration system, or CBC. It becomes more dynamic in terms of maintenance and fault diagnosis. And basically, with what I've described to you earlier, with enough knowledge of the system, with enough knowledge of the process variables and how they react to different conditions, you can train a model to automatically tell you if the calibration has drifted based on the historical data that's already available. You can also base that off of surrounding sensors, so primary and secondary instrumentation can tell you the kind of conditions that device has been seeing and whether it's likely to have caused drift in the system. There are, of course, costs associated with CBC as well. And just by implementing these kind of diagnostics, you're obviously going to have to pay either a data science company or your own engineers and data scientists to work on these models. Implementing digital networks to give you that level of data can also be quite a costly exercise if you don't already have them. Even training staff to understand and work with this new level of information can be a costly and a time-consuming thing. And crucially, if you're incorrectly interpreting this new system's data, so great, you've paid for a new system, you've got all this data, but if you're not using it properly, that in itself can be costly. So basically, it's a balancing act. For someone, maybe time-based calibration works perfectly well. There's no need to go to condition-based calibration. That's absolutely fine. But if you are looking to implement more efficient systems in line with a digitalisation strategy, as they're commonly known, then these are the things you have to bear in mind. There's also other considerations as well. So, certainly from our experience over the past 3 years, data ownership is crucial. It's been in the news quite a lot, but when it comes to data science projects in particular, and again in engineering applications, you need to ensure you have the rights to work with the data and share that data with a third party. The data may even reside on your server, but the results may be confidential, or it might have associated IP with it. So you may not even be able to work with it. And there's been a couple of cases in the past where this information has come to light quite late on in the process or in the specification process, and it can derail a project and delay it quite significantly if you've not got that information to hand early on. Another crucial consideration is availability. And what I mean by that is, do you even have the data that contains information you need to train a model? So if you're training a model to detect error states in your system, error state data can actually be quite rare, especially if you're not logging 100% of the time. If you're only logging during certain test points or calibration runs or whatever, it's very unlikely that you've got a large sample set of errors, because if you do see an error, you're typically shut down your system, correct it, and then start again. But having that error data is what ultimately trains your model to recognise the subtleties between errors, because an error is not going to happen the same way every time. There may be different pressures in the system, different temperatures, and there'll be subtle variations between all different process variables. So again, it's just something to bear in mind, that you may have to consider other ways of generating your data. So reproducing the data, for instance, in the field or within a lab, you could send, again, using a flow example, you could send a flow meter to NEL, and we could automatically detect these errors by installing them in our facilities, recreate the error you want to see, and generate that data. But of course, you're then paying for facility time, you're paying for data analysis, and it can be expensive. Or if you're wanting to even reproduce erosive flow, of course, at that stage, you're actually destroying a flow meter. So if you're putting sand through a meter and you want to detect through diagnostic variables when a flow meter is starting to erode, then you put the cost of the meter itself and the cost of the testing. So it can be expensive to reproduce error data to train a system. You can use synthetic data, which is a relatively new concept, certainly to us as a company. But effectively, synthetic data is data statistically generated to mimic the real data that you have. And it's a way of increasing your sample data set and effectively allowing your model to work with a larger sample size. So we've got a standard workflow that we have at NEL when it comes to data science. You've got defining your objectives. Seems like a simple one, even an obvious thing. But if you haven't defined your objectives ahead of your embarking on your data science job, then ultimately you're not going to get very far. What I mean by that is, by defining objectives, is being clear on what kind of things you want to automatically detect. Do you want to detect specific errors? Do you want to detect calibration drift? These things seem subtly different, but it does mean that you may have to use different models and you may, at that point, you'll understand what kind of data sets you need to either make use of if you've already got historical data, or collect new data, which is the next stage. So data collection and integration, collecting new data and integrating it with the historical data you already have, or merging it with synthetically generated data. And then once you've actually got the data and you've passed it over, the next stage is to do an exploratory data analysis phase. So look at how those data sets correlate with each other. Are there any key process variables which are crucial to detecting a certain state? That comes under the feature engineering stage. And then, of course, you then move on to actually developing the model and the solution. So there's, sorry about my voice failing me. I don't know what's happened. So yes, feature importance. As I said before, you've got different devices that can now, due to digital technology, output multiple variables. And it can be overwhelming, even for experienced engineers, to review that data. And especially if you're trying to relate those variables' response to a specific operating condition. So, as I've said earlier, just generating a model to explain to end users automatically a particular variables, or feature as we call them, importance to a particular scenario is a very useful tool. And some variables may be interdependent. Even quickly visualizing the correlations using so this is a statistical method known as the Pearson correlation, where you can trend your variables on the X and Y axis and see, and essentially map and cross-reference which variables under given scenarios are shown to correlate either positively or negatively to each other, and how strong that correlation is. And just, I suppose, to give you a couple of case studies to look at. As I said, we've taken part in a few projects now, either mining our own data or working with customers' data. Historical data is an incredibly useful data set to work with, usually because it's either well understood already, it's possibly already been reviewed by experienced engineers in a particular facility, and there's generally a wealth of information in the system. So for this particular example here, this was when we used some historical data to predict the remaining useful life of 3 different flow meters that were working in erosive conditions. So that was with sands present in a flow system, various concentrations of sand. We were given primary sensor data, so we had 3 flow meters, primary values. We also had the secondary instrumentation for that facility as well, so the pressures and the temperatures dotted throughout that facility, and all correlated and trended in time series data. And we also had additional diagnostic data from a third-party software that was running in the background that was specific to one of the manufacturers of one of the meters. So what we did was we trained a model to look at the data, to look at the correlations and how these meters were performing over time when exposed to erosive flow. And the model was trained not only to predict and determine actually the concentration of sand at various points based on all the variables, but also predict the remaining useful life, which is an incredibly powerful tool for any operator who's working with a particular meter who may have data already that's building up in the erosive flow. You can now forecast when that meter is either going to need replaced or brought out for, and serviced, recalibrated, etc. We've also worked with clients who want to do live data monitoring, so and detect known errors. So this is an example of a user interface we developed for a company who wanted to train a model that was to look for normal conditions, known errors and unknown errors. In this particular case, there was I think 5 to 6 known errors they wanted to detect, and they were able to over time point us within the label data when these errors occurred in the data streams. Therefore, we could train a model, and over time we were able to, again, talking to the customer, train that model to be more efficient in detecting these systems. And we ultimately produced a red, amber, green alert, which is at a basic level just telling an operator everything's working fine, there's a potential issue or there's a definite error in your system, and then not only tell them that, but also point to a specific error and even point to a specific diagnostic help file for a particular meter and how a technician might go about helping the other end users in the plant diagnose the problem or fix the problem. These kind of interfaces, of course, any software developer knows can be tailored to our clients' needs. They can be made simpler. We can add trends or anything that's of interest to them as and when required. The more complex side of things is the models that are going on in the background, and of course the end goal is to make it a seamless experience. The operators don't need to have any understanding of data science or even the data that's flowing into it, but simply viewing this data on a user interface is ultimately what they're looking for. It's worth pointing out, though, that there is no perfect model, and so a big part of the process that we undertake here when we start our data science job is we try different models. We look at the initial data sets that have been provided, even during the initial quoting stage, before we even started working full-time on a project or even signed a contract. Generally, we'll be given a sample data set to work with, and we'll try different models. We'll go back and forth with questions about the data itself, and try a few things. And that is incredibly useful as well, because before you even start on the project, you've got a feel for the data, what kind of models you're going to be using, and therefore what staff members you're going to be using in your team of data science and mathematicians, because people have different skill sets. Some people code in Python, some people code in R, some people have different experiences in different applications. So the initial specification and quoting stage and model selection stage is actually one of the most crucial stages. And again, coming back to that, defining your objectives as well. It's crucial that you get as much of that done up front before undertaking the job, because it will make things go a lot smoother further down the line. And just a summary of what we do here effectively. So again, the process itself, we look at the goals of a customer. They might be different things. So as I've already said, they might be looking to move from a time-based system to a condition-based system. It might even just be something like improving operational safety. So I've been talking about errors in the sense of detecting when a meter's misaligned, but it may be more critical than that. It may be flagging when it's a safety issue. But again, as I say, it may just be things like optimizing maintenance. So things like the calibration drift I was talking about, and detecting when a meter or an instrument is going to drift from its calibration, therefore reducing your unplanned downtime. The idea is ultimately as ever, is to reduce operational costs by implementing these kind of systems. But as I say, and it is crucial, if I would summarise anything, is one of the key challenges is the availability of data, the ownership, and of course access to it, and access to the specific data you need to train the model to detect the thing you're wanting to detect. So yes, a lack of failure data. But yeah, I mean, I'm talking about things from a two-sided perspective, but ultimately, anyone who's involved in this kind of work, who's involved in data science and data analytics, typically they can provide support and look at discovering patterns, and data scientists and mathematicians and engineers across the world are all beginning to realise now that working together is the best way forwards. You know, you don't just feed a data scientist information blindly. You work with an engineer who understands the sensor or the application, and overall that gives you a much better support package. Certainly we think so anyway. And it gives you much more actionable information and insights. And in our case, there may even be sensors that are installed and maintained by supervised. And ultimately, what we're doing now is offering predictive analytics solutions, but there is no off-the-shelf predictive analytics solution as far as I'm concerned anyway. It's very much a back and forth with the customer and something you would develop over time. So you go back to one of the earlier slides I had about the 4 different stages or 4 levels of a data science project. It's likely that you'll progress through these 4 levels with a client before ultimately arriving at the predictive analytics stage. So there's different next steps that you can undertake, and certainly if this what I've spoken about in terms of the initial steps you have to take for data analytics before building a data-driven model, feel free to get in touch with myself or anyone at Supervised for that matter. If there are any data analysis opportunities that you'd like to discuss with us, it's worth pointing out in particular that certainly from our point of view as a lab who's part of the National Measurement System, there's something in place just now called the M4R, Measurement for Recovery, which was put in place to help small businesses recover from COVID. Ultimately, what that allows businesses to do is apply on a simple form on the website, which is the link in blue in the bottom right there. And if the application is accepted, it entitles you to 20 days free consultancy from any NMS lab, depending on the application you're providing, you're applying for. You can have 3 projects per company, which actually translates to quite a lot of time when you think about consultancy fees and so on and so forth. So certainly if you have a particular data science application that you can think of, then by all means get in touch and we can talk you through the process of filling out the M4R form and see if your project is something viable that we could help you with. And I think that's it from me. So I'll hand back over to Sarah now, and we'll start looking at some questions and answers.
Thank you, Gordon. We've got a few questions in, so we'll just start running through those.
Sure.
I'll start with the first one. Has your team had a need to generate synthetic data for any projects you've delivered?
Yeah, so that's a good question, and yes, we have. So as I say, having data which is representative of error conditions is very rare. So on 2 or 3 projects, what we've had to do is bulk out those data sets with, okay, there's an initial couple of data sets which do contain the error states that you want to detect, but that's not enough to train a model to reliably detect that every time. So what we've had to do is build these synthetic data sets, which, as I say, they basically statistically mirror the patterns and the observations in the original data sets, but they also include subtle variations in terms of the different variables that you've got. So again, pressures, temperatures, densities, or whatever. And that gives your model something more to work with, and it can train itself to look for these subtle variations. Because if you feed it very limited sample sets on a particular error where the pressures and temperatures are exactly the same both times, it's just going to look for that condition again and again. But if you train it using this synthetically generated data, it just gives you more to work with. Of course, ideally, the ideal scenario is to have live data which is representative of the errors. But as I say, it's very rare to find that. Or when you start suggesting how to generate more of it, the costs quickly pile up. So synthetic data generation is something we're looking at for a number of our research projects, not just commercial jobs, but certainly for our research projects as well. Because we ourselves, we don't want to destroy our own systems. We're the national standards for flow measurement, so we don't want to destroy our reference systems. We want to generate as much data as possible. And synthetic data generation has helped us in previous projects, and we're getting quite good at it. So that's the plan, is to continue to do that. And as I say, now that we're getting very good at it, the plan is to roll it out to our commercial services as well, and help customers bulk out their data sets if that's something that they're looking to do. So yeah, hopefully that answers that particular question.
Okay, thank you. And another one, your examples have been around sensor data. How applicable is what you've discussed to other types of data? We have a lot of vehicle tracking data.
Okay. So yeah, as I say, I tend to go towards my own experience, which is in sensors and flow measurement, but ultimately data is data. And certainly a lot of the data scientists and mathematicians that work in my team, they're not engineers themselves. They have a background in engineering now, and they have an understanding of the systems, having worked with us for so long. But ultimately, the methods that we use here can be applied to any data set. So again, it comes down to data visualization or pattern recognition as a first off. So for vehicle tracking or vehicle data, I mean, off the top of my head, you would have information possibly on GPS coordinates, or maybe checkpoints, or time spent at a checkpoint. So you might be looking at a data science project where you're trying to improve your efficiency by looking at how long a particular truck spends at a particular checkpoint. Is there a better way to optimize the routes if you've got multiple vehicles out on the road at one time? So yeah, it's not limited to your traditional process plant sensors. It can be anything. It can even be text data. It can be anything where a pattern can be drawn out. And ultimately, if you can detect patterns, then you can potentially improve upon those patterns if you apply your own knowledge and experience to them. Okay, hopefully that one.
And another one. How long does this data prep stage typically take?
So everything I've spoken about here is variable depending on the application itself, and how much the customer understands their own data first. So if you're dealing with a customer who understands their data, who's curated it, labelled it, and are ready to go, then it can be a very short process. It can be a case of a one meeting where they explain exactly what they want to do, and off you go. It's unlikely that's the case. In which case, it depends on the size of the data and how well curated it's been. Has it been labelled? Has it been well structured? Are there gaps in the data? Are we going to have to generate synthetic data to fill gaps in terms of detecting known errors or detecting whatever? So there is no clear numerical answer to that, but I would say everything I spoke about today is not particularly complicated. The idea is, as I say, this is the taking a step back webinar before you dive into the deep dive data-driven modelling webinars, which we've done in the past. Is to give customers an idea of what needs to be thought about before jumping into talking to a data science company, because I guarantee you, whether you talk to us or anyone, the people on the other side of things will have these kind of questions ready about what kind of data have you got, how much data do you have, is it labelled, because the decision tree inside these people's heads is going to be cascading. So it just helps knowing going in that you'll be asked these kind of questions. But if I was to say any time at all, I would say it shouldn't be long, assuming that the right people are talking to each other, essentially.
Okay, I think we've got time for one more.
Sure.
Does the digital data lag impact the digital flow rate accuracy? And if so, then how to prevent it? As for the case of fiscal measurement system, that number may affect a lot of the revenue.
Yeah, no, it's a very good question. It's something we're thinking about here just now. So at the moment, we're almost at the transition stage where most flow meters that are in service or that we see coming through here, they have an analog output on them. So you rarely see a digital only meter, although we are starting to see more of them now. And yeah, you're right. That can affect things like fiscal measurement. At the moment, we're still able to calibrate all these meters because of the analog output that comes with them. But as I say, this webinar is funded by Bayes, and we do a lot of flow program research for Bayes. One of the projects that we've got in with them is a project looking at this very thing, where we're looking to upgrade our facilities to deal with calibrating digital-only meters, either using gravimetric calibration methods or proving methods. So again, where you're looking at triggering of signals versus reference meters. So I can't give you an exact number about how that affects the data, because we, as I say, we ourselves are about to commission a project where we look at this in a lot more detail. But I suppose any kind of assurance I can give just now is that from what we've seen, the flow meters that we're seeing come through all have analog outputs, which are typically what's calibrated and used in the fields, and the digital value seems to be used as the verification versus the analog. It's more for information or feeding into process control systems, which is more for information only as opposed to physical purposes. But no, it's a good question, and as I say, it's one that it's very, very interesting to me and some of the technical leads here. And as I say, the plan is to build a facility that ultimately deals with that, but also researches the exact and quantifies the exact numbers that we're talking here.
Okie doke. I think that's about
okay.
Got today. So thanks for joining us, everyone. As I mentioned earlier, we will send a copy of the presentation out to you. And if you need any more information, you can visit our website, which is www.tufsud.com/en-gb if you need any more information. And thank you to everyone for joining us today.
Yep, thank you very much.